Hi, I'm Benjamin Woodruff, and I'm here to talk to you about JavaScript and what's awesome and what isn't awesome about it, and how to fix the stuff that isn't awesome. So, um, so my background, I did an internship at Facebook last summer, and I worked on the JavaScript infrastructure team, and as part of that, I moved Facebook.com over to ESLint from JSHint. They're two different linting systems, and I'll talk about that more in a little bit. It's fine. So first of all, why JavaScript? There's a lot of reasons why you would want to pick JavaScript. But personally, I think the most important reason here is that Hacker News likes JavaScript, so therefore you should use it. And so in this talk, I already went over that. So we're going to start with just programming language theory. So in programming language theory, you have, if you're doing a compiler, you have a bunch of steps. You have code, you convert that to tokens. You convert those tokens to an abstract syntax tree. You do various constraining over it. Then you transform that into some sort of different format. And then maybe you eventually interpret it. And some of those steps can kind of be skipped over, but we're just going to talk about all of them. So in the first two steps, you have Lexing and Parsing, where you convert the code to tokens, and then you convert those tokens to the abstract syntax tree. And so here's an example of how Lexing would work. Here you can, a lot of times when you do Lexing, you define it as just a bunch of regular expressions, and then you just match those against a string. So here I match this string against the bunch of different tokens, and then you get an output of a bunch of different tokens. And then you can actually remove some of those tokens that aren't semantically important to the language. For example, white space and comments, and then that can simplify things later. And then you have to take those tokens and you have to convert them to a tree format so that it can be more easily traversed. And so the easiest way to do that is called recursive descent parsing. So here you just have a top-level parse function, and then that top-level parse function calls a parse statement helper function a bunch of times, and it builds up a program that's the whole body. And then in parse statement, you have different types of statements. So it looks at the next token in the token stream and tries to figure out what it should go into to parse, and so it predictively parses. And then in addition to statements, wrong screen, you have code in order to parse functions, and you have function keywords, and then you can actually consume certain tokens like parentheses and curly braces and just make sure that they're there and then just throw them away. And so you could do that, and you just keep going on, and that's how you build up an abstract syntax tree. And the details of that aren't super important, but and then the problem that you encounter here is that that ends up being a ton of code, and you don't want to write that all the time, and good programmers are lazy. So since we're compiler writers anyways, let's make a new language that's shorter for defining this stuff, and then let's make a compiler for that language. So we do that, and you end up with something like this. So this is Peg.js, which is a parser generator system in JavaScript. And this is that same program, that same syntax converted to Peg.js syntax. And then it actually ends up not being too long. And it may not be totally legible if you're not familiar with Peg.js's syntax, but it's pretty compact, and you get a lot of stuff in there. And actually, so this entire thing here, we can copy it. I'll just retype it. And we can take it and we can stick it in Peg.js. There we go. And so now we have a full parser. And so we can take our language, and in our language we define a statement as a function or call expression. So let's start with a call expression. And so we'll just say, and so now, just by writing the parser over here, And by writing the code over here, you end up with an abstract syntax tree. And you can add, this thing has a way to define functions, and so you could do that as well. And it also does nice error output. So if I don't put a parentheses there, it says expected, close parenthesis, or expression, but end of input found. So it actually even adds nice error messages for you in that nice, tiny, compact syntax. But there is a problem here. Some programming languages, the way that the constructs are defined, they can't be parsed entirely using this context-free grammar parsing system. So there are hacks to get around that. So as an example, indentation-based languages don't have clear curly braces to start and end blocks. So there's no token explicitly to match on to figure out when you should stop parsing a block. So the solution is to add a stack to the lexer and then have the lexer handle it by inserting indent and dedent tokens. And this is how languages like Python and Coffeescript do it. And you can actually try this. So this is Python 3 code. And this is actually the output of using the tokenize module in Python 3. And those are the actual tokens that Python uses. So you can actually try this at home. It's really cool and really easy. OK, so back to where we were. We covered tokens and abstract syntax tree. Now we'll move over to constraints. So in order to have constraints, there's various things you can do in a constrained step. JavaScript doesn't really have one because it's not a compiled language. But you can do type checking. You can check that variables are defined in a symbol table. You can verify argument counts, various other things. And this is what we're going to make the linter do when we talk about that step. So JavaScript, no JavaScript talk would be complete without a slide talking about all this stuff that's bad about JavaScript. So there's a lot here, and it scrolls too. So yeah. If you're interested in the bad things about JavaScript, there's a great book called JavaScript, The Good Parts by Douglas Crawford, and he talks about all the stuff that's bad in JavaScript, plus the stuff that's good, all the stuff that's bad. So in order to fix this, we're going to take that constrainer step that was missing in JavaScript, and we're going to add our own in there. And we can also use the next generations of the JavaScript specification, which are ECMAScript 2015 and ECMAScript 2016. 2016 hasn't even been finalized yet. 2015 has been, but we can use them already in browsers today. And we'll also minify our JavaScript so that it doesn't take up as much space when you're downloading it to the browser. And another option is don't write JavaScript in JavaScript. You can compile other languages to JavaScript, so we'll talk about that too. So round one. So we're going to start talking about minification because it's the easiest thing to do, kind of. And the obvious way that you could easily go about doing this very quickly, very easily, is you don't even build an abstract syntax tree. You could just tokenize it. And then remember how we threw away that white space in the comments when we were talking about tokenization earlier? They aren't semantically important. You could just throw those away, and you get most of the benefits that you would get of JavaScript minification. But you still miss a bunch of really easy places to compress. So the way modern minification works is you build an abstract syntax tree from the tokens, and then you do find and replace on certain syntactic elements in the code with just shorter ones. Like if you have undefined, you can replace it with void 0, which is a few characters less, but does the same thing generally. You can also mingle local variable names, so you just replace them with shorter ones. And you can remove code that's obviously dead, like if you have if false, you just delete it. But if false doesn't really work too great. If you want to have better dead code removal, you kind of have to do some better static analysis. But it turns out with JavaScript, that's really hard because it's a dynamic language. So for example, here you have this object, and it has 2 entries in it. And if you are dynamically getting one of the things inside of that object using introspection, which this code is doing, then you can't figure out if you can remove any of those entries in the object dictionary. So this kind of ends up being pretty difficult, and sometimes, in certain cases, trying to do static analysis of certain things ends up being equivalent to the whole new problem. So the solution is to make a bunch of assumptions about the code, like not using introspection there, and also to optionally add annotations to turn on and off some of the static analysis assumptions. And this is what the Google Closure compiler does. And then there's a moderate improvement because of that, but it is a lot of extra work because you have to add a bunch of annotations, and it can end up breaking code in weird ways that you don't expect. And so as a result, it ends up being usually avoided. But that doesn't mean it's useless. So now we have a problem. So we want to parse this stuff into an abstract syntax tree, but how are we going to get that abstract syntax tree? So the way that people used to do it is they would just write their own parser, and they would build their own AST, and they would have their own AST format, and they just use it. Naturally, people want to come up with one standard that satisfies everybody's use case, so we have one. So now there's ESTree, which is a standardized abstract syntax tree format for JavaScript, and it has a specification document and everything. And it's essentially derived from Mozilla's internal SpiderMonkey format that they were using for JavaScript. And so now we have a bunch of parsers. Some of them are really, really fast parsers written in JavaScript. So there's Esprima and Acorn, which both use the ESTree format. There's some forks of them that add some more modern language features and extra stuff like React support. And then there's also some other parsers like Shift, which is a newer parser that has a different AST format that's still interesting. So there's this really cool website that's built by a Facebook employee, not me. And it has this thing where you can write code on the left, and then you can actually see the tree on the right. So this is actually an iframe here. So we can actually like jump through the code, and we can see how the abstract syntax tree is formed. And it can be really useful for debugging different code that uses JavaScript abstract syntax trees. If you're trying to write linter rules and stuff, you need to go through the abstract syntax tree and try and match on things. So it can be very useful for debugging. And it also has support for a bunch of different parsers that you can jump between. And so you get different trees and stuff. Click off the iframe. So the next step is that we're going to go to after minification is linting. Linting also doesn't really require anything other than the abstract syntax tree, so that's why we're going to it. And linting at its core is very simple. You just pattern match parts of the abstract syntax tree, and then you generate warnings based on those matches. That's all you do. And so this is an actual lint rule that's in ESLint, which is a popular linter. And they just match on every time there's a member expression. And if there's a member expression that has a console in the front, so like console.log, then every time it matches on it, it can give a warning and tell you unexpected console statement, because maybe you don't want to have console.log in production code. And so you can, that can be very useful. And there's a lot of popular linters. JSLint was really the first popular one. That got forked into JSHint, which was designed to be a little bit more flexible. JSHint kind of muddied the waters, though, by, well, JSHint wasn't totally responsible for it. There was kind of muddying of waters between stylistic concerns and correctness concerns. So now JSHint tries to only do correctness concerns, and they moved the stylistic concerns into a separate project, JSCS, that uses a more standardized, it uses the ESTree AST format, but JSHint, because it's derived from JSLint, which is really old, doesn't use the ESTree format, so there's a lot of confusion there and stuff. And then there's also ESLint, which is also popular, and it's kind of competing with JSCS and JSHint, because it does both things in one package. And maybe in the future, Babel, which I'll talk about a little bit later, may add support for it, because it kind of overlaps in certain areas of what it has to do. So in addition to just doing pattern matching, Another common thing that you want to do in a constrainer is verify static typing. JavaScript doesn't have static typing, but you can add it. So there's TypeScript, which is Microsoft's project that adds, it's a language superset of JavaScript, and you can add annotations, and it does type inference and everything. There's also Flow, very similar approach. And there's also the Google Closure compiler, which uses magic comments to try and do it, but it's not quite as robust specifically for static typing. It's just like an extra feature that they add in, and that makes their advanced optimization feature work better. So as an example, this is ripped from the Flow website. They have, you have a function foo, and here they actually don't have any type annotations yet. And if you just run Flow over it, you can get benefits immediately, because it notices that you're passing in a string to function foo, and then function foo is multiplying that string with an integer, which doesn't make sense. So then it generates a warning automatically. And then multiplying a string with an integer is not, it's not Python. So. And then you can then optionally add type annotations that help with the type inference. And so here they add string and number type annotations. And then it generates a different warning message because it gets a little bit further in the progression of analysis. So back to our chart, we've covered code, tokens, the abstract syntax tree, the constrainer, and now we're going to cover the transformer. So there's a great language that you may have heard of if you haven't been living under a rock called Coffeescript. Some people don't think it's great. I heard a sigh. It uses the JSON Python generator. So I talked about Peg.js. JSON's another popular one. And JSON is designed to be like Bison, except in JavaScript. And it changes the syntax, but not really the semantics so much. And the nice thing about this is it kind of shows how easy it can be to write a compile to JavaScript language, because the code for Coffeescript is actually really simple. And I suggest looking at it if you're interested in compilers. And because it's a fresh start syntactically, it can fix a lot of JavaScript issues. Like JavaScript has equals, equals, and equals, equals, equals. And since Coffeescript doesn't have to try and be backwards compatible with equals, equals, it can just drop it and just use the strict equality. And it was actually very influential in the development of the ES 2015 standard. So that's interesting. But there's a problem that people always bring up with Coffeescript, which is if I'm debugging, my console is going to warn in the wrong places, and I'm not going to know where the code is, and I'm going to have to look at the compiled source code and try and map that with what the actual source code was. That was a problem for a while. It was really bad. But now, every web browser has this great thing called source maps. And so here it's actually happening with CSS, but the same thing happens with JavaScript. I just found this GIF that somebody made. And so the console is actually showing a line number in there that's in the SCSS file that's compiled to CSS. And when they click on that, it actually maps them to the right place. And it does this with all sorts of stuff. So if your JavaScript code throws an exception, it can map that back to the original location in the Coffeescript file. So it's really cool. And this can actually, source maps can survive several compilation steps. So you can have Coffeescript to JavaScript, and then you can do JavaScript and minify it. And that source map can be preserved the entire way through, which is really nifty. So enough with Coffeescript. Let's talk about JavaScript. So there's the JavaScript ES 2015 standard, formerly known as ES6, or ECMAScript 6. And so as a motivating example of why you would want to use it, here's just one feature in the language, which were awful. Okay. And in modern JavaScript, you have promises, which jQuery supports. So we can use .then. And then here we actually use an arrow function. So this is a shorthand function syntax that was stolen from Coffeescript. And we can shorten that code up a little bit. I think I noticed a syntax error, but I'm not going to point that out. And then in ES 2016, which is the next generation standard that's not finalized yet, they added support for async and await, which were stolen from C#. And so now you can take this promise code and you can actually turn it into something where you say data equals await $.ajax, and that works. And that actually works with any code that uses promises. It's really nifty, it's really cool, and it's not in any browser yet, which is our problem. Not in any browser yet. But there's a solution. So there's a lot of JavaScript to JavaScript compilers. Flow and TypeScript we talked about because they're supersets of the JavaScript language. So when you compile them, they just strip out the type annotations. But there's also Google's Tracer, and there's also Babel. And those are next generation to previous generation JavaScript. So you can actually take that async await code that I had in the previous slide and compile it with Babel and then run it on Internet Explorer 8, and it works. Babel adds all sorts of language features, and it also interacts with React and Flow correctly, so that's really cool. So you can use all this stuff together. But enough about JavaScript. Do you guys miss pointers like, asterisk and ampersand and C and?
So.
Well, there's a way to compile C code and C++ and anything that uses LLVM to JavaScript. So here's an example of Box2D running in JavaScript, and it works and it's performant enough. I don't know, there's some frame dropping, and it uses WebGL, which is also nifty technology. And there's also other cool stuff you can do. So I don't know why this is. Try and refresh. All right, here we go. So this is actually Python compiled to JavaScript running in the browser. So we can actually take this, we can just hit run, and now we're running Python in the browser. So you can have your multiply string stuff. Although the performance hit is horrible because you're running an interpreter and an interpreter. But
it's Python 3.4.
But we'll the next slide is about the performance. So there's this thing called ASM.js, which is a subset of JavaScript that Mozilla came up with a while ago. And it's strictly typed, and it has ways of dealing with a simulated heap and stuff. But it's also technically a subset of JavaScript. So you can take this and you can compile your JavaScript code to it. And then Firefox has lots of optimizations in it to make this faster. And it's a strict subset of ES3, which means that it works on every browser in existence pretty much. And it's fully sandboxed, so you can run arbitrary executables that are written in C and not have to worry about security issues. And it's ahead of time compiled, so it's fast. And to quote some of them, the ASM.js website, it's usually within a factor of 2 slowdown over native compilation with Clang. So it's fast. So there's one little missing piece here. I talked about the abstract syntax tree. I talked about the transformation. And then you get that to JavaScript somehow, but like what's in the middle? How do you do the abstract syntax tree and then actually convert that back to real code? So there's 2 obvious ways. Well, one obvious way, one less obvious way. There's string concatenation. You can just concatenate on the abstract syntax tree that you have and match on everything. Or you can use something that somebody has already done that does string concatenation, and you can use an AST reprinter. And that can also do smarter things like dropping extra parentheses and stuff. So Recast is one of those. It's probably the most popular one. And you can take an abstract syntax tree, just pass it to it, and then ask for the code, and it'll just give it to you. And so you can do some really cool stuff with Recast, because we had this website that we've seen before, but it has an extra little feature in here for transformation. So we can do JS code shift, which uses Recast in the background. And then you end up with these extra 2 panes. And so the problem that you're approaching is we have this big code base, Facebook, and you you want to change some sort of behavior in all of the code all across Facebook. So what you can do is you can write this tiny little thing. So there's this 11-line script over here on the bottom left-hand corner. And it just takes all identifiers. It matches on identifiers. And every identifier it sees, it just reverses the string, something silly. And then you end up with tips gets converted to spit. And print tips gets reprinted to spit, turn, whatever. But you can programmatically do transformations in your code, which is very powerful, especially when you're converting between older JavaScript variants and newer JavaScript variants. And then it's also cool just to see in this tool, you can take the code right here, and you can immediately modify it in browser. And now we have an underscore prepended to every identifier. Pretty cool, right?
Is this done live as they're serving JavaScript, or is this something that's done as like a?
This is happening on your browser.
But I mean, like people using this, are they transforming JavaScript live?
Well, you do this as a way of testing your transform code, and then once you get your transformer working, then you take that and you actually run that over your code base. Yeah.
So you ship the underscore spit code.
Yes, right. Except you don't I don't know why you would ever reverse identifiers.
In fact, if it ends in like a number, you probably don't want to
Right.
reverse it.
Also, another cool thing about Recast that I didn't mention is Recast preserves the parts of the AST that you didn't modify. So there's no concern about formatting getting screwed up, which is really cool. All right. So, takeaways. Modern JavaScript's pretty cool. It has a lot of faults, but you can work around them. And as a compilation target, it's really cool because you get C code in the browser. I mean, how much cooler does that get? So, questions?
So how do you leverage NPM modules?
Oh, wait, we should use them.
Oh yeah.
How do you leverage NPM modules with this sort of tooling?
Right, yeah, that's a good thing that I should have had a few slides on. You can use a compiler that compiles modules to a single file, puts them all together.
So something like Browserify?
Like Browserify, or there's a lot of options for that, but I should have had a slide on it. Sorry, I didn't. Yes, that's an issue because JavaScript doesn't have modules by default in the language, and you can add them. And in fact, the JavaScript ES 2015 standard does add support for them with the assumption that you're going to use it with a compiler. Oh, I thought you were.
I actually do have a question. Do you hate the fact that JavaScript has now become a compiled language?
No, I think it's great.
You do? I hate it. Build steps are the bane of my existence.
Well, so JavaScript's always kind of been a compile target ever since people had large JavaScript code bases, because you have the module issue. That's kind of hard to get around. So people always had the compilation step, at least, of let's concatenate all these JavaScript files together. And at that point,
Yeah.
you've already lost. So, yeah.
In the original Kernighan and Ritchie C, functions could have local variables, but they had to be scoped to the entire function. You couldn't have a variable declared in a block. When I learned JavaScript, it had something like that, but even worse. You could put a variable in a block, but it still was scoped to the entire function. So if somebody showed me a block of JavaScript and said, does this do what I think it did? I'd have to say, well, that depends on what is anywhere else in the entire text of the function. That was like maybe 3 years ago was the last time I dealt with that. Is that fixed now somehow?
Yeah, it is.
And
There's
how's it fixed?
let and const keywords that do proper block scoping, and that's in ES 2015, and you use Babel, you can use it in any browser today.
I think your functions are too long. That should not.
Well, yeah, exactly. I mean, if you put every line of code inside its own lambda, then even in the original JavaScript, you'd solve that.
You don't just have let, you also have const, so you can define constants as well in block scoped form.
Is the issue there hoisting?
Yes.
Yeah. Now, there still is function hoisting whenever. I mean, you can use function expressions to do that if you want. But.
So I was just like, one observation is it seems like there's a lot, like it's difficult. It looks like it's more and more difficult to talk about JavaScript as like one thing, right? Like you like, oh, what do you work on? Oh, I do a lot of JavaScript programming. It's like that could be anything, right?
Right.
Right. But it also seems like there's so much variety that like it's interesting to think about it relative to like how other languages are sort of managing their evolution, right? Like, and to use to like think about one particular example, like Java like never changes, right? And like there's like NCC 92 or whatever that never changes, and then JavaScript is changing so quickly that it's almost becoming like a virtual machine platform where like real JavaScript source is not even really like a language anymore.
Right? ASM.js.
Right.
Nobody's going to write that by hand.
Right. So I wonder like, do you feel like that's made it harder to, while it's given you a lot of like browser compatibility, do you feel like it's made it more difficult to also, because you have all of these different frameworks and you have things you want to integrate, and like you know, in a language that's not changing much, you pull the library and like you can mostly read it, right? But like if there's something written in like Python compiled to JavaScript and you're like, oh, I'm going to use that library for this and this for that, like it seems like you have to start to know a lot of breadth of tools that have names that like could be anything.
Yeah. So I think while JavaScript's never going to stop changing, I feel that a lot of the issues that we have are kind of short term and will kind of stabilize on some sort of thing eventually for a lot of the choices. That's already kind of happened in some areas, and I feel like that will kind of happen more over time. And I think it's better for the long term that we do have a lot of different implementations, because that means that we can try a lot of things quickly, whereas in Python maybe that doesn't really happen as much, for example, because all batteries included. For example, Python was stuck with async core for the longest time, which is really horrible framework, and that's only just now been replaced. But other languages that can iterate more quickly have been doing a lot more innovative things.
Other questions? No?
So I've played a little bit with Scala, making Akka actor projects for a class, and I've heard some stuff about the multi-threaded nature of JavaScript as web. Well, I hear some people do stuff with web workers, but I don't know if they're actually multi-threaded or what's going on there.
Yeah, there are web workers, but they don't really work the same way as pthreads do, because there's no sharing between the different threads. It's that you aren't allowed to share data structures between. So.
But is there preemption? Is there
web workers are preemptive threads, I believe.
It's more like Unix processes, like pthreads.
Okay.
Right. Exactly. So there is I think there's a proposal that they're trying to get in that will help ASM.js, that will allow it to emulate pthreads properly. But that's not really here yet, sadly.
Thank you.
I was going to ask you, at some point this could actually mean that like Java and JavaScript could be like synonymous, right? Like someone could actually start compiling them to each other?
Actually, that's already been
and
done.
Is that, well, or is that, how does that make you feel?
Oh. Well, so Google has Google Web Toolkit.
Right.
That's been around for a while.
It has.
I think it's acceptable. If you want to do it that way, I'm not going to stop you. I'm just not going to join you necessarily.
Yeah. Cool. Other questions? No? Anybody? All right. Well, thanks.